Lecture 8 talks about the probability measure to go along with our probability models. Last time we introduced the probability measure as a mapping from our script A to the range 0, 1. Remember, script A was our collection of all subsets of our sample space. We had that for any event in our script A, then the probability of the event is always greater than or equal to 0, and it can be equal to 0. The probability of the entire sample space is 1. And if we have two events in our script A that are disjoint, then the probability of the union is just the sum of the probabilities of each individual event. So using these axioms of probability, we want to figure out probabilities of complements, unions, intersections. So here, if we know what the probability of an event is, then what is the probability of its complement? So let's look at some of the things that we know. We know that if we take an event E and we union it with its complement, then it has to equal the entire sample space. And that E intersected with its complement is always equal to the empty set, just based upon what is the complement of E. It's everything that is in S but that is not in E. So by definition, the complement in itself is empty set, the intersection of it. So the probability axiom, remember it told us that the probability of the entire sample space is 1. So that gives us the probability of E union EC. But we also know that E intersect with its complements, the empty set. So we also have that the probability of the union is just the sum of the probabilities. So substituting in this up here, we have that 1 is equal to probability of E plus the probability of the complement. We can just solve for the probability of the complement, and we get that it's 1 minus probability of the event. Okay, so now let's talk about unions. If we have two events, E1 and E2, we want to know how to define the probability of a union of events. We already know from the probability axiom that if E1 and E2 are disjoint, then the probability axiom simply gives us that the probability of the union is the sum of the probabilities. Okay, so now what if we have the situation in which E1 intersect E2 is not the empty set? So this is the picture that gives an example of E1 union E2 not the empty set. So notice here we have some that overlaps. This is our E1 intersect E2 and it's not empty. Okay, but note what we can do here. We can rewrite E2. We can write E2 as this intersection here between E1 and E2. And then we can also write this other part as the intersection of E2 with E1 complement. Because remember, E1 and E1 complement always make up the entire sample space. So since we have that E1 complement intersect E2 and E1 intersect E2, so this part here and this part here are disjoint, then we can say the probability of E2 is the probability of the union of these, right? These two are disjoint sets, so we can say this is the sum of the probabilities. Rewriting, we have that the probability of E1 complement intersect E2, so the probability of this part, is equal to P of E2 minus this part, minus the probability of E1 intersect E2. Okay, so let's see what else we also have. We also have that if we look at the union between E1 and E2, so the union between E1 and E2, this is E1, this is E2, so their union is going to be this part plus this part. Well, it's simply E1 union with this part that was not in E1, so remember this was just our E2 intersect E1 complement. And we have that E1 and this E1 complement intersect E2 are disjoint, so if we look at the probability of E1 complement intersect E2, it's just, and we also had this in the previous slide, then when we look at the complement of E1 union E2, we can look at the probability of E1 plus the probability of this other set. This is what we found on the previous slide. So the probability of the E1 complement intersect E2 could simply be written as P of E2 minus P of E1 intersect E2. So now we have a formula for unions. If we have two events, E1 and E2, and we take the union of them, then probability is going to be the sum of the probabilities minus whatever is in common. So if this is the empty set here, the probability of the empty set is always 0. So this would be back to our axiom of probability. Okay, conditional probability. Suppose I roll a die and I tell you that the outcome is odd. So now you have some additional information. This is what's called conditional probability. I don't tell you I just roll a die. I tell you I roll a die and I give you some extra information in it. So given the extra information that the outcome is odd, now what is the probability that the outcome was 3? Okay, so what does the outcome being odd tell us? It tells us that now our whatever we rolled on our die has to be either a 1, 3, or 5. So now it has to be contained in this set 1, 3, or 5. Each of these are equally likely, so what's the probability that we get a 3? Well, all of these have equal probability, so each of them have a probability of 1/3. The probability of getting a 3 is now 1/3. Okay, so now I told you that the extra information was the outcome was odd, so what's the probability that the outcome was 2? Well, remember the probability of the outcome being odd means that we have to be in the set 1, 3, or 5. 2 is not in that set, so the probability that the outcome was a 2 is now 0. So let's see if we can kind of refine this a little bit to give us some idea of what we use in general when we know some information. So in the previous example, we knew that we had some subset. So instead of knowing that we had the whole sample space, we knew that we had some subset. So we knew we had the odd numbers. So how do we update our probabilities when the outcomes are only in W and not in all of S? Okay, so let E1 and E2 be two events. Then we can define the conditional probability of an event E1 given event E2. So the way that you denote this is the probability of E1 given, this line stands for given, E2. And the formula for this is just you look at the intersection between E1 and E2 divided by the probability of E2, provided that this probability is positive. Okay, so now let's go back to our example. Suppose I roll a die and tell you the outcome is odd. What is the probability that the outcome was 3? So remember here, the conditional probability says that I want to look at the probability of the intersection over the probability of what I already know. Okay, so probability of getting a 3, given the fact that I rolled an odd, here this is my odd set, is going to be equal to the probability of the intersection divided by the probability of what I know, the probability of this 1, 3, 5. Well, the probability of 1, 3, 5, that is, remember that's 1/3, 1/6 plus 1/6 plus 1/6 gives me a 1/2. The intersection between these two sets is just the 3. What's the probability of having a 3? Remember our entire sample space is 1, 2, 3, 4, 5, 6, so the probability of getting a 3 is just 1/6. Do the arithmetic and you get 1/3. Now again, with the other example, what was the probability that it was a 2? So where do we get the 0 from? Well, up here in the top we have the intersection, we have the empty set when you intersect these two, so the probability of an empty set is always 0, so we just get 0 here. Another definition, two events are called independent if knowing one of those events doesn't affect the other one. So probability of E1 given E2 has no effect on the probability of E1. So it's the exact same. Probability of E1 is the same whether or not I know what happened with E2. More generally, we say that E1 and E2 are independent if we can write their intersection as this multiplication, as probability of E1 times probability of E2. So let's think about flipping a coin and rolling a die. What is the probability of rolling 6 given that we flip heads? So we have the event of rolling a 6 given the fact that we have flipped a head on our coin. So our sample space, if we look at our entire sample space, right? So we flip a coin, we can get heads or we can get tails. So here we have all of our heads, and here we have all of our tails. So we could flip heads or tails. When we roll our die, we can get 1 through 6. So here we have a head with a 1, a head with a 2, etc. Tail with a 1, tail with a 2, tail with a 6. That's our sample space. So what is the probability of rolling a 6 given that we flipped heads? So here's that heads and 6. Here we have 12 possible events in our sample space, all of them with equal likelihood. So the probability is just going to be 1/12. Now let's examine the fact that these are independent events. So basically, let's just show the probability of the intersection between E6 and E8. I can just simply write it as probability of E6 times the probability of EH. Okay, so let's look at what E6 is. E6, the event that I roll a 6. So how do I roll a 6? I roll a 6 by, I can have a heads in a 6 and I can have a tails in a 6. Probability of heads, I could have a heads with 1, 2, 3, 4, 5, or 6. So these are two events, and we want to show that they are independent. So let's start with the probability of E6. I look at the union of these. Probability of the union, these are two disjoint sets, so I can add the probabilities. Probability of each event is 1/12, so I just get 1/6. Again, these are all disjoint sets, so I can just add up the probabilities. All of these are 1/12, so I just get a 1/2 when I add them all up. So the probability of E6 given EH, so I look at E6 intersect EH. The only thing that's in common between E6 and EH was heads and a 6. The probability of EH, probability that I'm going to roll a heads, I can roll a heads half the time. So 1/12 over 1/2 is 1/6. This is the probability of E6. Right there. Moreover, if I look at the intersection between the two, the intersection is just H6. Remember I said this is just 1/12. There's 1/12 probability I'm going to get this. I can write that as 1/6 times 1/2, which is my 1/12. So probability of E6 times probability of EH. The law of total probability. So if you can write a sample space, if a sample space can be partitioned into a collection of disjoint events, then E can be expressed as a disjoint union, E intersect E1, union E intersect E2, union, etc., etc. So here we have our sample space S, and it can be written as a collection of sets, E1, union E2, union EK, so that each of these events here are disjoint. Remember, that's what the definition of partition means. If we know the conditional probabilities, so we know the probability of E given each of these EIs, then we can use it to find the probability of E. So this gives us the law of total probability. So here, this is just what I said. If you can write S as this union, each of these are disjoint, then how can we get the probability of E? The probability of E is just going to be the sum of all of these, because these are all disjoint, right? But what is the probability of E intersect EI? Well, we saw that on a previous slide. It's the probability of E given EI times the probability of EI. Okay, so let's do an example. So if you have a standard deck of cards, the probability of a random card is that one of the cards is hearts is 13 out of 52. Because there's 4 different suits, it's 52 cards. So the probability that you pick a card, you have 1/4 probability of picking hearts. Now suppose that you have a deck that's missing one card, and a card is picked from the deck. Now what is the probability that it is a heart? Okay, since all cards are equally likely, and all 4 suits are equally likely, then we can say that the likelihood that the missing card, the probability of the missing card as a heart is just 1/4. Okay, so now let's verify this. Let H denote the event that the card is picked as a heart. So then we have M is the missing card as a heart, and so the complement is that the missing card is not a heart. So think about our sample space. Our sample space, we're going to have M union MC. So either the missing card's a heart or the missing card's not a heart. So we have M union MC. So we have some disjoint union here. So we can write the probability of heads as the probability of heads given that the missing card, the probability of hearts, not heads, sorry. Probability of hearts given that the missing card was a heart times the probability of the missing card was a heart plus probability of a heart given that the missing card is not a heart times the probability that the missing card is not a heart. Okay, so if we look at the probability of getting a heart given that the missing card is a heart, so now we only have 51 cards, right? And if we're saying the probability of the missing card, we know the missing card is a heart, that means we only have 12. Probability of the missing card being a heart is 1/4. Those are 4 suits. Okay, probability of the card picked is a heart given that the missing card is not a heart. So remember we had 51 cards. The missing card is not a heart, so we have 13 hearts left. And the probability that the missing card is not a heart, there's 3 other suits, so that's going to be 3/4. Add this together and you get 1/4. Okay, Bayes' rule is the common rule. So suppose we know something about the probability of E2 given E1, the probability of E2 given E1 complement, and the probability of E1. How do we find probability of E1 given E2? So basically, we have this, and we want to know this. Okay, so by definition, we have probability of E1 given E2 is the probability of the intersection divided by the probability of E2. So, think about, this is also, so if we just kind of reverse this, by definition the probability of E2 given E1 is again the probability of this intersection divided by probability of E1. This again is by definition. But the E2 intersect E1 is the same thing as E1 intersect E2. Exact same thing. So what this implies is the probability that E1 intersects E2 here is equal to just cross multiply probability of E1 times the probability of E2 given E1. So that kind of goes up there. So now we have the probability of E1 given E2. We have probability of E1, something we know about. We have the probability of E2 given E1, something we know about, but we don't know about the probability of E2 yet. Okay, so what do we know? We know that we can write E2 as the union between these two disjoint sets. We can say it's E2 intersect E1, union with E2 intersect E1 complement. So the probability of E2 is just the sum of these individual probabilities. So the last slide, remember we knew something about this intersection. So this intersection we can write, this first one we can write as the probability of E2 given E1 times probability of E1. This one we can write as the probability of E2 given E1 complement times probability of E1 complement. That's what we derived on the last slide. What's the probability of E1 complement? Remember we derived that earlier. That's just 1 minus the probability of E1. So now we have probability of E2. We put that in the bottom here. So now everything is in terms of something that we know about. So we get Bayes' rule. It's complicated, it looks complicated, but it's a way of figuring out what the probability of E1 is given E2, knowing all this other information. So how do we do this? So let's consider a test for disease. Suppose you know that the probability of testing positive if you have the disease is really high. So it's 0.999. But the probability of testing the disease given that you don't have the disease is 0.01. So if you don't have the disease, you only have 1% probability of testing positive. The probability of having the disease is 0.1. So what is the probability a person has the disease if they test positive? In other words, what's the probability that you have the disease given test positive? Just the reverse of this, right? So what's the probability of testing positive given you have the disease? But really what we want to know is what's the probability that if you've got a positive test that you really do have the disease. Okay, so if E1 is having the disease and E2 is testing positive, running this kind of in our more mathematical terms, then we want to know what the probability of E1 given E2. This is just, we're going to use Bayes' rule. We have all this information, so let's kind of write it in terms of what we have. E1 is you have the disease, E2 is you test positive. So what's this say? This is the probability of having the disease times the probability of having the disease, of testing positive given you had the disease, probability of testing positive given you had the disease, probability of having the disease, plus probability of testing positive given you don't have the disease, and 1 minus the probability of having the disease. So if you go back and you look at what you have on the other side, probability of having the disease we have was 0.999. Probability of testing positive given that you had the disease we said was 0.1. So here we have those filled in. Probability of testing positive if you don't have the disease, we had that on the previous slide also. And we had the probability of having the disease, so we can take 1 minus that. So you get about 92% probability of having the disease when testing positive. So there's an 8% chance that you don't have the disease. Let's look at the positive side. Okay, so now after you finish lecture 8, you're ready to do assignment 2. You have all the techniques that you need, and it's due Friday, September 12th at midnight. And let me know if you have any questions.